can light push things? So not just heat things up, but actually exert real physical force. This is the idea of radiation pressure and how electromagnetic waves carry momentum and can actually deliver force. We already know that electromagnetic waves carry energy, but energy and momentum go hand in hand. So if electromagnetic waves can deliver energy, they must also be able to deliver momentum, right? And they do, because when light hits a surface, it applies a tiny force called radiation pressure. And radiation pressure is defined as the force per unit area that's caused by light. It was predicted by Maxwell from Maxwell's equation, and it follows straight from the conservation of momentum. So here's how momentum transfer works. When light hits a surface and it delivers an energy of U, the momentum transfer depends on how the wave interacts. If the light was fully absorbed, the momentum is given with this formula. The energy divided by the speed of light. But if it was fully reflected, then it's given with this formula. It's the same thing, but we multiply by 2. Why double? Because reflection is like bouncing a ball. So the momentum change is reverse, not just stop. How about going from momentum to pressure? So using Newton's second law, by the way, this is how Newton's second law was originally stated. It was in terms of momentum. Change in momentum over change in time. This is the rate at which momentum changes. So radiation pressure becomes, when it's fully absorbed, pressure equals intensity over speed of light, and when it's fully reflected, the same thing times 2. Intensity is the energy per unit time per unit area for a wave. So all of these formulas are on the free cheat sheet in the description, and let's go through an example problem with them. A powerful laser beam delivers 2000 watts per meter squared onto a perfectly reflecting surface. That's the intensity. It gets shot onto the surface and perfectly reflected. Let's find 2 things. A, what is the radiation pressure? And 2, how much force is applied to an area of 0.01 meters squared? Let's start by finding the radiation pressure, which is with this formula when the light is fully reflected. 2 times the intensity, which is 2000, given at the beginning, from here, divided by the speed of light, which is 3 times 10 to the power of 8. The answer is 1.33 times 10 to the power of negative 5 inches per meter squared of pressure, if it's fully reflected. How about the force that our laser beam applies on an area of 0.01 meters squared? This is a very small spot to hit. And force is equal to pressure times area taken from the pressure formula but rearranged. And this is equal to pressure, which we just found as 1.33 times 10 negative 5, multiplied by the area, which is 0.01, giving us an answer of 1.33 times 10 to the power of negative 7 newtons. This is a tiny force, but it's very real and it's there. And here's a really cool application. Have you ever heard of solar sails? So this light, we can actually use it to push spacecraft through space, just like how we use wind to sail boats. Imagine a large reflective sail, and the area is 1 kilometer by 1 kilometer. The sunlight, and it's in space, and the sunlight from very far away, it delivers an intensity near Earth of 1000 watts per meter squared. The radiation pressure, given with our formula, 2I over C, is 2 times the intensity, 1000, divided by speed of light, 3 times 10 to the power of 8, which is equal to 6.7 times 10 to the power of negative 6 newtons per meter squared. With this information, are we able to find total amount of force pushing on our solar sail? Let's find the force with our force formula. Force is given by pressure times area. Pressure, which is 6.7 times 10 negative 6, times area, which is 1 kilometer times 1 kilometer, which is 10 to the power of 6 meters squared, equals 6.7 newton. This is a small force, but on a 1,000 kilogram spacecraft, this builds up because of acceleration. Take a look at Newton's second law. Newton's second law, F equals ma. It's famous, right? We can rearrange for acceleration to find A equals F over m. And let's see the acceleration that our force is creating. So 6.7 newtons multiplied by the mass of 1,000 kilos. This is 6.7 times 10 to the power of negative 3 meters per second squared of acceleration. Over time, this will continuously add up to speeds of hundreds of thousands kilometers per hour. This is how real-life missions are designed to work, using no fuel. They use light as the propulsion. It's futuristic, it's awesome, and there's 2 companies you can search up if you want. This one is this one, and the second one is this. You can have a look at what they're doing. I think this is some awesome science technology. And if sunlight can push a sail, then a laser can push a molecule. Radiation pressure is used in biology labs to steer microscopic objects using focused laser beam. This is what's called optical tweezers, and these are used to move DNA strands. They're used to hold bacteria in place, and we can measure molecular forces. Even though the pressure is tiny, at atomic scales, the force is huge. So here's a final wrap-up of everything we talked about. Electromagnetic waves carry momentum as well as energy. This momentum delivers a force when light hits something, and this creates radiation pressure. This is the final idea in electromagnetic wave theory, and this was the last topic video I'll ever upload on this channel. So if you watched every single video I've ever made up to this point, you will have a full textbook's worth of physics knowledge. All that's left is to solve problems over and over again until you become a supercomputer human genius megamind weapon.